Hey there, and welcome. Today, we are diving deep into the world of amines. Now, these are a totally essential class of organic compounds. I mean, they're the building blocks for just about everything, from medicines to dyes, so really getting a handle on them is key. You know, the easiest way to wrap your head around an amine is to picture its parent molecule. Good old ammonia, NH3. Seriously. Every single amine out there, no matter how wild and complex it looks, can trace its roots right back to that simple little molecule. They're all just ammonia, where one or two or even all three of those hydrogens have been swapped out for a carbon group. So let's really lean into this whole family tree idea to see exactly how this works. And it really is a super logical progression. You start with the parent, ammonia. If you swap out just one of its hydrogens for a carbon group, bam, you've got a primary amine. Swap out two, well, now you've got a secondary amine. And you can probably guess the next step. Replace all three, and you've made yourself a tertiary amine. It's that straightforward. The number of carbons directly bonded to that nitrogen tells you the whole story. Okay, so now that we've got that basic structure down, let's zoom in on the two major ways amines get classified. And this is all based on the kind of carbon group that's attached to the nitrogen. And this lays out the fundamental difference so clearly. On one side, you've got aliphatic amines. That's where the nitrogen is just hanging out with a simple, open carbon chain. But on the other side, you've got aromatic amines, where that nitrogen is attached directly to a super stable ring structure, like benzene. And trust me, this one little difference completely changes the game for their chemical properties. All right, so we know what they look like, but what about their personality? You know, what do they actually do in a chemical reaction? So let's just boil it down to one question. What is the one single chemical property that pretty much defines everything an amine does? And the answer is they're basic. More specifically, they're weak bases. That just means they really like to accept protons, but they don't, hold on to them with an iron grip or anything. So the big question is why? Why are they basic? Well, it all comes down to the nitrogen atom. See that little pair of dots right there? That's what we call a lone pair of electrons, and this little spot of negative charge is just sitting there, ready and waiting to reach out and snatch a positively charged proton from a molecule nearby, like water. That very reaction, that's the heart and soul of their basic nature. But okay, here's where things get a little more interesting. Not all amines are created equal when it comes to being basic. The strength of this basic personality really depends heavily on the amine's overall structure. And to really get why, we need to quickly talk about the three main factors that can either crank up an amine's basicity or dial it way down. First up, we've got something called the inductive effect. I want you to think of those alkyl groups, the carbon chains, as being really helpful little friends. They have this natural tendency to kind of push their electron density towards the nitrogen atom. And what this does is make that lone pair even more negative and even more ready to leap out and grab a proton. So more alkyl groups generally means a stronger base. But then there's the steric effect. Okay, imagine trying to get to the snack table at a super crowded party. It's tough, right? Well, that's exactly what a proton trying to reach the nitrogen in a big, bulky tertiary amine has to deal with. Those same alkyl groups that were so helpful electronically can physically get in the way, just blocking the proton's path. This crowding effect actually makes the amine a weaker base. And finally, we've got the resonance effect. And this is a huge deal for aromatic amines. So in a molecule like aniline, that lone pair of electrons isn't just sitting there on the nitrogen. No way. It's actually being shared all around the entire benzene ring to make the whole molecule more stable. And because that lone pair is so busy being part of this resonance, it's just not available to go grab a proton. This is the big reason why aromatic amines are so much weaker as bases than their aliphatic cousins. Okay, so we've got their structure, we've got their personality, but how do chemists actually build these things in the lab? Let's take a look at one really clever method. This is the Gabriel phthalimide synthesis, and it's broken down for us into three main steps. Now, what makes this reaction so cool and so useful is that it is an incredibly clean and reliable way to make only primary amines. You don't get messy mixtures of secondary and tertiary products. By following this very specific path, chemists can build the exact primary amine they're looking for, pure and simple. All right, let's do a super quick recap of the big ideas. Number one, all amines are children of ammonia, and we classify them based on how many carbons are attached to the nitrogen. Number two, their defining chemical personality is being a weak base, and it's all because of that lone pair of electrons.
And number 3, how basic they are comes down to a balancing act between electron pushing groups, physical crowding, and resonance.
And I'll leave you with this to chew on. If we know that an amine structure has total control over how basic it is, just think about how important that must be for designing new medicines. How could a chemist tweak and tune the structure of an amine in a drug to make sure it works perfectly in the very specific pH environment of the human body? Something to think about. Thanks for tuning in.